are doing that, and we are very grateful to all the resource persons from universities, colleges, institutes for kindly sparing their time and making these lectures possible. And also, we have been conducting these talks in Kannada with the intention of encouraging Kannada in higher education. So this is essential simply because that is the language, the natural language in the state, and most people feel comfortable in that. And ultimately, we have to switch over to that, whether you like it or not, isn't it? So think about that. So we are trying to make an effort in that direction also. So we are very grateful to Professor Suvrat Raju from ICTS TIFR. I welcome him to the program for kindly agreeing to talk about this very interesting topic of quantum gravity. We all hear about that, but we don't know much about it. So he's one of the experts in India in the field of quantum gravity, and he has kindly consented to give a introductory talk about the quantum nature of gravity. So before I request him to talk about the subject for about 50 minutes, followed by 10 minutes of discussions, I would like to give a brief introduction to him, since we are not very familiar with, most of you may not be very familiar with him. Professor Suvrat Raju got his BSc honors from St. Stephen's College, Delhi, and then went on to get his PhD from Harvard University in the year 2008. After that, he came back to India and became a postdoctoral fellow at the Harish Chandra Research Institute. He stayed there for 2 years and then became a Ramanujan fellow there for another 2 years. Then he joined the ICTS, International Center for Theoretical Sciences, TIFR, in the year 2012 as a reader, and he became an associate professor there in the year 2017. And since 2022, he is a full professor there in the ICTS campus of TIFR. He has held several visiting appointments. He was a visiting assistant professor at Brown University in 2012 and adjunct faculty at Harish Chandra Research Institute in 2013, between 2013 and 15 for 2 years, and Cheng Visiting Fellow, Harvard University in the year 2015, and Simon's Associate, International Center for Theoretical Physics, ICTP, in Italy, for a 5-year duration, 2019 to 24. And he has been awarded several prizes, recognitions. He won the St. Stephen's College Centenary Medal in 2002, Ramanujan Fellowship of the DST in 2010-15, during 2010-15, NASA Young Scientist Platinum Jubilee Award, awarded given by the National Academy of Sciences in 2013. And he was the INSA Young Scientist Medalist in 2013. He won the Saraswati Kaushik Medal of TIFR in 2015 and Swarna Jayanti Fellowship DST during the period 2018 to 23. And he was awarded the ICTP Prize in 2019. And more recently, he was awarded the Nishina Asia Award given by the Nishina for Memorial Foundation in the year 2022. So we are very thankful to Professor Raju for sparing his time. So he's going to talk about how does information emerge from a black hole. Now, Professor Raju, you can take over.
Okay, thank you very much, Professor Kagali, for that kind introduction. Thank you very much to all of you for joining on a Sunday morning. So I'm going to speak about this topic of how does information emerge from a black hole. But really, as the professor mentioned in his introduction, this is really talk about quantum aspects of gravity and about how gravity when you combine the principles of quantum mechanics and gravity together, you end up with some rather remarkable phenomena that are relevant for black holes, but that are more generally also relevant in the study of quantum gravity. So I'm going to, I should say before I start that, I was not completely sure about the audience. And so I prepared it based on the understanding that, that Professor Kagali gave me. But if you have any questions, please feel free to stop and interrupt me. And I'd be happy to explain more. So, so we can have an interactive session. So as I said, this talk is primarily about gravity. And so I wanted to start with the most basic thing that all of us know about gravity, that all of us teach in school, which is the Newtonian force law. And the Newtonian force law, which was, developed to understand the motion of celestial bodies, the Earth and the Sun, for example, tells us that if you have two objects, for instance, you might have the sun here, and this blue dot is the Earth, then there's some force between them, which is proportional to a constant, which we call the Newton's constant, and the product of the masses and the inverse square of the distance between them. So this law was, this rule was understood many years ago, 350 years ago, and it's been a remarkably successful theory. In fact, in some sense, the theory of this theory of gravity is almost, a quintessential example of a successful scientific theory. And that's because although this was developed to understand the motion of planets and the sun and so on, it actually applies over a wide variety of scales. It doesn't always happen that you develop a theory that works in some regime and the same theory works in a different regime. But this is true with gravity, this theory. So for instance, when we have rocket launches, for instance, ISRO, which is in our city, launches a rocket, there is almost everything they want to know about this rocket can be computed by using this Newtonian force to understand the effects of gravity. Similarly, although this rule about the force was developed to understand the attraction between the sun and the earth, if you look at the earth and the moon, and this is a picture of that, then the same rule applies with excellent accuracy also to earth and the moon. And of course, the same rule also applies, in the rooms where we are sitting. So it's this rule that we have, which is that, the gravitational force between two objects is proportional to the product of the masses in the inverse square of the distance, is a very, very successful rule. Okay, so that's why it is, we still teach it 350 years after it was developed. However, about 100 years ago, a little more than 100 years ago, and maybe 125 years ago, people started realizing that there was something slightly strange about this Newtonian force law. And one way to think about it is to think about the following thought experiment. Okay, so this is a thought experiment. It's a bit of a joke, of course, which is, imagine that some giant comes and moves the sun, or more realistically, maybe some, alien civilization comes and moves the sun a little bit. So you could then ask the question of, this is the Earth, and when does the Earth know that the sun has moved from the place it was in originally? So the sun has moved, and therefore the distance between the Earth and the sun has changed. And if you remember, the force law was the statement that the force was proportional to the product of the masses and the inverse square of the distance. However, the distance has changed, and therefore it would seem, if we believed the Newtonian force law, that the Earth would immediately feel a change in the gravitational field of the sun, and therefore the Earth would, feel that effect immediately. However, we realized about 125 years ago, the work of Lorentz and Poincaré and Einstein, that this was in contradiction with another feature that we were discovering about the world, which was that information does not travel faster than the speed of light. So it doesn't happen that if you're given if you move the sun, that immediately that force or that information that the sun has moved should be transmitted immediately to the earth. So the Newtonian force law, which, as I emphasized at the beginning, is in fact a very, very successful rule, was in contradiction with this other thing that we learned about nature, which is that, the speed at which information is transmitted is bounded by the speed of light. And the Newtonian force law is in contradiction with that idea, because it suggests that the force is instantaneously changed because the distance is instantaneously changed. So, of course, to correct this, first the formalism in which this was understood, as all of you will know, was first understood in the context of the theory of special relativity. And then, people understood how to generalize the Newtonian force law itself to be consistent with this principle. And that is what is called the theory of general relativity. Now, the actual quantitative predictions of general relativity are only very slightly different from those of Newtonian gravity. In fact, I believe that just last week, you had a talk by Professor Bala Iyer, who works on, observational consequences of general relativity. But, the reason we have to work so hard to extract the observational consequences of general relativity is that in almost all settings, those consequences are very weak. However, the ontology of general relativity, or rather, if you ask the question of the objects that general relativity speaks of, that is very different from Newtonian gravity. So, even though we started with this simple principle that, information shouldn't travel faster than the speed of light, by the time the theory of gravity was made consistent with this principle, and also with another principle called the equivalence principle, the theory was very different from what it had been originally. So the theory of the modern theory of gravity, of general relativity, now does not speak of the force between the sun and the earth. Rather, the theory says that both the sun and the earth are embedded in the fabric of space-time. So they're both embedded, and we speak of the space-time in which they live as itself being a dynamical object. And then, the what the theory tells us is that the presence of the sun or of the mass warps the space-time, or rather curves the space-time in its vicinity. And then the reason the Earth moves in an orbit around the sun is not because the Earth feels a force to the sun, but rather because those orbits, those are just the natural orbits, are just the natural trajectories. They are like straight lines, they're geodesics in this curved space-time. So, as I said, the language that we use to describe general relativity is very, very different from the language that's used to describe the Newtonian theory. And of course, it's not just language. There are some precise equations that go along with this. These equations were developed by Hilbert and Einstein, and they tell us that the curvature of spacetime is captured by something called the Einstein tensor, is proportional to what's called the stress energy tensor of matter. But more simply, this just tells us that this term T, doesn't matter what the details of the equation are, captures the influence of matter, in this case the sun, and this tells us how the space-time has to respond. So the right-hand side tells us about matter, and the left-hand side tells us about the response of the space-time. And then, if you want to understand, given the space-time that has been curved by the sun, how the Earth moves in this space-time, then you use this equation, the second equation, which is that in a certain space-time, you have a certain equation of motion for matter, and therefore space-time tells matter how to move. So these are the equations that go along with the words of general relativity. And as I said, we have this rather broad formalism in which we have introduced these auxiliary quantities about the space-time fabric in which the Earth and the sun live. And, this theory is now consistent with the principle that I told you at the beginning, which is that information cannot travel faster than the speed of light. So if we go back to the question that I asked, with which I started, which was what would happen if a giant were to move the sun. So here's our friendly giant, is back. In the theory of general relativity, the answer is that when the giant pushes the sun, that doesn't lead to a change in force, because now we don't speak of forces any longer, but rather, this movement of the sun disturbs the space-time, and that causes ripples in the fabric of space-time. And these ripples propagate at the speed of light. And when they propagate at the speed of light, it takes 8 minutes for those ripples to reach the Earth. And it is after that that the Earth knows that the sun has been displaced from wherever it was originally. So this is how the theory of general relativity makes things consistent makes the gravitational force consistent with the relativistic principle that information cannot be transmitted faster than the speed of light. And these ripples, even though I've drawn here a cartoon, are actually quite real. So in the talk that you had last week, the gravitational wave research into gravitational waves is really all about detecting these ripples when they come from cosmic collisions very far away from us. And those cosmic collisions lead to ripples which take a long time to reach the Earth. And then we are able to detect them. So this theory really has been verified in many, many different ways. I'm now going to go on and talk about black holes and other consequences of the theory. But maybe before I do that, if there are any questions here, it would help me get a sense of whether I'm being able to communicate what I wanted to say or not. So just to summarize, what I introduced so far was just that we have a very successful theory of gravity, which is the Newtonian theory. It's extremely successful. However, there is a quirk in the theory, and something which is fundamentally, conceptually incorrect about the theory, which is the theory suggests you have instantaneous action at a distance. And therefore, we have had to correct the theory. And we have this new modern understanding of gravity, which is that, matter tells space-time how to curve, and space-time tells matter how to move. And this new theory, is both quantitatively and qualitatively consistent with what we understand about nature so far. Was there a question?
I just have a small comment, if you don't mind.
Yes.
You are showing the picture there of a giant trying to push the sun or whatever into the black hole.
Yeah.
So this very idea of pushing should not be there. There must be some kind of the very presence of the giant should be sufficient to cause the movement of the sun. Is it? Is it not?
Yeah, that's true. Yeah, that's true. This is, of course, the cartoon. This is not. This is just meant partly as a joke. But you could imagine a different kind of situation where maybe on the other side of the sun from where we are, there is some supernova explosion, and the ray, the influence of that supernova first reaches the sun, and then reaches us. So if you wanted to be more realistic, this is something that you could imagine, where you have some influence which is coming. So if the Earth is here, there's some influence that's coming from the other side that pushes the sun. And so, it's not impossible to have something that changes the trajectory.
Yeah, I understand. Very small comment only. Yes, please continue.
Yeah. Are there any other questions about this?
So please continue.
Okay. Yeah, I'm just waiting to see, just to see if people are getting what I said so far, or if there are any other comments about the question. I would really encourage you to ask them, because it'll really, since there's Zoom meeting and I can't see most of you, it would help me a little bit. Yeah. If if there are any questions, just to make sure I'm communicating what I want to say.
Yeah, no questions. Yeah.
Okay. So I'll assume that that this was clear, and I'll go forward. After people understood the theory of general relativity, people started investigating it mathematically. And very soon after the theory was discovered, the German mathematician Karl Schwarzschild found some exact solutions to the theory. And those exact solutions to the theory go by the name of the Schwarzschild solution. I've written the solution here, but in fact, the details of this is a non-technical talk, so the details of the solution are not very important. Rather, what Schwarzschild found is what is in modern terminology called a black hole. So this black hole, the metric that I gave previously tells you what the space-time of a black hole is precisely. But you can think in cartoons in the following way. The black hole spacetime is a spacetime that's slightly different from the spacetime as it looks around us. So if you go very far away from the black hole in this region, I hope you can see my mouse, then things look like they're basically flat. And as you come closer, you reach this surface, which I've plotted here, this region, and this is called this occurs at a point which is 2 times the Newton's constant times the mass of the black hole divided by c squared, where c is the speed of light. And at this point, there is what's called the horizon of the black hole. And the horizon of the black hole has the significance that once an object is inside in this black region, then it's impossible, at least classically, and I'll say something more quantum mechanically, but at least at the classical level, it's impossible for the object to exit from this region back into ordinary space, which is this red region. So the horizon of the black hole is this region here. And then as you go deep, so once you're inside, you're forced by gravitational forces collapse, further and further to go to smaller and smaller values of r. And in fact, once you reach r equal to 0, that's what's called the black hole singularity. And that's where, all matter gets crushed by gravitational forces. However, in this talk, I won't have much to say about the singularity. It's just going to be about the fact that the black hole has this horizon, and this horizon is a point of no return. It's like a Rubicon. So once you enter it, you cannot exit it. And this horizon has a size which is proportional to the mass of the black hole. And there are some constants, but the constants are not so important. So this is one of the first solutions that was found to the Einstein theory. But in fact, many years after this solution was found, is there a question? Okay. Many years after this solution was found.
No, there was a question about the horizon.
What is the question?
The question is, what exactly is the horizon?
Yeah, the horizon is just, it's an imaginary line we draw in space-time that demarcates two different regions of space-time. So the horizon is not something which is are these questions on the chat? I cannot.
Yeah, chat only. Yeah, somebody asked a question.
Okay, yeah. If I can't look at the chat, so if you could just tell us, take a look, and then why is the screen yeah. So yeah, just please tell me if there are questions. So yeah, the horizon is not something which is locally visible. Rather, it's a region of space-time. It's like a Lakshman Rekha, but you can't see the Lakshman Rekha. So once you cross the Lakshman Rekha, you can't go back. But it's not, so there is a region of space which has that property, which is once you're here, you cannot exit. But locally, when you're crossing it, there is nothing that would tell you that you have now crossed the horizon. So it's like an invisible Lakshman Rekha. Once you've crossed it, you're trapped inside. But locally, you can't do anything that will tell you that you're trapped. So it's not like physically there's a wall or there's something that exists there. But rather that there's just a region which once you enter, you cannot exit. And you don't know that you cannot exit till you have entered.
Yeah.
Okay. Are there any other questions about this?
No, nothing more.
Okay. Okay. So what I was saying was that many years after this Schwarzschild solution was discovered, it was in fact, the black hole solution was not really taken very seriously. Even if you open, say, something as recent as the Feynman lectures of gravitation, there are misunderstandings about the black hole, and there isn't, this isn't really taken seriously. But now, we understand black holes much better. And in fact, black holes have now been observed in many, many different ways. So, for instance, we know now that there is a black hole in the center of our own galaxy. And the way we know it, of course, is not by looking at the black hole itself, but by looking at the motion of stars about the black hole, which tells us that they're orbiting this extremely dense object. And a few years ago, the Nobel Prize in Physics was given for this discovery, which is that there's this black hole called Sagittarius A star. And this black hole is extremely massive. It's about 4 million times as massive as the sun. And it's far away. We are kind of at the periphery of the galaxy. So this black hole is, 26,000 light years away from where we are. Is there a question?
No question.
I think somebody has raised their hand. Rudra Swami.
He wanted to know how is the black hole mass related to Chandrasekhar limit or something like that.
Good. So that's a separate question. That, in fact, I'm about to say a little bit more about how that black hole is formed. So indeed, it's true. Here I said the black hole is 4 million times the mass of the sun. If you look at, I'll say a little bit. Maybe I'll postpone that question a little bit. Roughly in brief, the answer is that if you look at the way black holes are formed from stars, and then the way black holes are formed is that you take a star, and the star starts collapsing under its own gravitational mass, and then there are these limits which tell us whether the collapse of the star stops.
Continue. Also, it's disturbance. Yeah. Please continue.
I think I was muted. The sharing has also stopped.
No. It's possible.
Oh, okay. Yeah. So what I was saying was that the point is that for a black hole to be massive enough to collapse under its own weight, it has to be more massive than the Chandrasekhar limit. But that's only one possible mechanism for black holes to form. In principle, black holes could form under other circumstances, maybe at the beginning of the universe, and could be much smaller than the Chandrasekhar limit, as in fact I'll say in some time. So there's not that's a limit on what kinds of black holes or what kinds of can be formed in a particular kind of mechanism. But theoretically, black holes can be much smaller than that, as I was saying. Okay, so what's special about this kind of black hole that was observed some time back? Not observed some time back, that these kinds of black holes that we've seen around, and also I'm sure the lecture you had last week discussed the collision of black holes far away. What's special about these black holes is that there's a lot of paraphernalia about them. I mean, the reason we know about the existence of Sagittarius A star is because there are a lot of stars at the center of the galaxy, and these stars are going round and round, and it's by looking at their orbits that we know that this black hole exists. However, when theorists like me think about black holes, we think about what I like to call vanilla black holes. Okay, so the kinds of situation we like to think about is that maybe there's a star, or as I said, maybe there isn't even a star. There's some other gas of gas of dust, which is and this just exists in splendid isolation in the universe. And the reason we like to think about this is because, as you know, in physics, we often like to think of isolated systems. So, we'll often talk about a mass and a spring and talk about the mass and the spring by itself. And we'll imagine that the mass and the spring is the only thing that exists in the universe. Of course, realistically, if you really do any experiment, there are many other things around it. But it's useful often to consider isolated systems. And therefore, for the rest of this talk, I'm going to consider this setup, not the astrophysical black holes, which in fact are interesting because of what surrounds them. That's why we can do the astrophysics. The astrophysics of them has to do with these planets and accretion disks and so on that surrounds those black holes. However, I'm going to talk of much simpler black holes, or at least, which already are interesting enough to lead to theoretical questions. And these are just black holes where you start with some gas of dust, and the gas of dust is originally large. This dashed line here shows the horizon. Shows the size of the horizon of a black hole with the same mass as the gas of dust, and this gas of this gas starts collapsing, and when it collapses, at some point it becomes smaller than the horizon size, and once it does that, then no force in the universe can stop it from collapsing further, so it just keeps collapsing further and further till it reaches a singularity. So this is the process I'm going to have in mind, that at some point there was some gas, and this gas, collapsed, and it collapsed and it formed a black hole, and there is nothing else for now in the universe. This is all there is. So this is the kind of vanilla black hole that I want to talk about, which I'll now tell you some more interesting things about. Okay. So this is another picture of the same process where I described the collapse of the gas of dust. This is the same diagram, but rather than drawing cartoons where you show snapshots of what's happening in time, it's useful to just think of drawing a figure where time runs along the y-axis. So in this figure, time is running along the y-axis. So initially, this gas was spread out over some large region. So space is along the x-axis. As you go further and further, it becomes more and more, compressed, and eventually, it collapses to this singularity. And this purple region is the size of the horizon. So this horizon is here, and you see at this point, this is where the black hole, all the dust is inside its own horizon. Okay, so the horizon, in fact, starts forming before the dust is completely collapsed. And after you wait for some time, there's this horizon, and the dust has just gone inside and has collapsed to the singularity. This kind of collapse is called, Oppenheimer-Schneider collapse. Although interestingly, there was an Indian physicist, actually a Bengali physicist, called B. Dutt, who worked out many of the equations that led to this a few years before the paper of Oppenheimer and Schneider. And these processes of black hole collapse, in fact, were also clarified greatly by the work of Professor P.C. Vaidya, and also A.K. Rai Chaudhary, who showed that these singularities have to form. So there's really been a lot of contributions by Indian physicists to understanding this process. Now, in this diagram, I told you that time runs on the y-axis and space runs on the x-axis. But in fact, it's convenient to make some further change of coordinates. And these kinds of, it's the same diagram essentially, where time runs on the y-axis and space runs on the x-axis. But it's convenient to rescale space and time so that light rays are 45-degree lines. And also, it's convenient to do transformation so that, do a coordinate transformation. Coordinate transformation just means, rather than using the usual coordinates x and t, you use some function of those coordinates to describe points of space and time, just so that you can draw the diagram in a compact region, as we have done here. So these kinds of diagrams are what are called Penrose diagrams. And the special property of the Penrose diagram is that any light ray is a 45-degree line in this diagram. Okay? So a light ray is one where time goes as fast as space, and that's a 45-degree line. So this is the same process that I showed you earlier, where you had some gas of dust and it collapsed. It is in fact collapsing, even though in this picture it looks like it's spread out, but in fact it's collapsed to hit the singularity. This is the singularity, and this purple line is the horizon. There was a question earlier about what is the horizon. This diagram actually makes it clear what the horizon is, as it tells you the horizon is in fact a light ray. And that is why you cannot cross a horizon once you go on the other side of it. It's not because there is some force that prevents you, but rather because the horizon is a ray of light. So, once a ray of light overtakes you, there is no way you can catch up with it. If I shine a ray of light in front of me, I'll never catch up with it, ever. And that's exactly why once you enter on this side of the horizon, the purple line is the horizon, you cannot exit because you cannot catch up ever with a ray of light. So this is yet another figure of the picture of black hole formation. Okay, are there any questions about what I've said so far?
No questions, I see.
Okay. Okay, so our friendly giant is back. Our giant comes back whenever we need the giant to do some thought experiments. So, we can ask the following question. So you remember I said there was a black hole and the black hole was in isolation, but now we want to do a little bit more. Okay, so we call our giant back and we tell our giant to throw in a little bit more matter into the black hole. So maybe the giant takes the Earth and throws it into this black hole that has been formed. Okay. So you could ask then, what happens to the black hole? So we had this black hole that I just described, and now we summon our giant and tell the giant to throw in a little more stuff into the black hole. So what happens? So it turns out that after the formation of a black hole, if you throw in additional stuff, then of course the mass of the black hole changes, but the mass and other properties of the black hole change in a very specific way. So this is a diagram of the process I just showed you. You had this gas of dust that collapsed, and then this is the addition. This orange line is the additional stuff that was thrown in. And of course, this matter that is thrown in, if we are thrown into a black hole, we'll eventually end up at a singularity. This is our fate. This red line is a singularity. But the mass of the black hole changes. And remember, I told you that the area, that the horizon was proportional to the mass. Therefore, the black hole grows a little bit. Now, when people analyze this process in detail, they found something rather interesting. They found that these black holes obeyed some pretty interesting rules. In particular, if you looked at the change in the mass, so this is dm in this additional process, and it's dm because we throw in some matter. That change in mass is much smaller compared to the original mass that was there. So you look at dm. It turns out that that's proportional to the change in the area with a constant of proportionality that's called the surface gravity, kappa by 8 pi. And then there are additional work terms. So in work terms means that if the black hole has electric charge, then there's a term that's proportional to that. If the black hole has angular momentum, then there's a term that's proportional to the angular velocity times the angular momentum, and so on. But since all of us teach thermodynamics, this is also very reminiscent of the first law of thermodynamics that tells us the change in internal energy is TdS minus PdV and other terms which also exist if the object we are looking at is electrically charged or has angular momentum and so on. Okay? So, we have this analogy between the first law of thermodynamics and the behavior of black holes when they're perturbed. But what is more, there's a second property of black holes that's similar to thermodynamics, which is that in thermodynamics, remember that the entropy of an isolated system can never decrease. However, it only increases. And that's exactly what happens also for black holes, which is that the area never decreases. Now, you might have thought that black holes should obey a property that the mass never decreases. But in fact, that's not true. There's a process called the Penrose process, which can be used even classically, doesn't require any quantum mechanics, to extract mass from black holes. But, even in that process, the area of the black hole always increases. Okay? So we have this analogy between the laws of thermodynamics.
What exactly do you mean by area? You mean the area of the horizon, is it?
The area of the horizon. Thank you very much for that clarification. Yes, exactly. When I speak of the area of the black hole, I mean the area of the horizon. Because the horizon is what demarcates the boundary of the black hole.
Yes, sir.
Okay.
There is a question from the audience.
Yeah.
How black hole actually attracts other objects?
It's by the gravitational force. You could think of it in general relativistic terms, where the black hole space-time is a certain warped kind of space-time. In that space-time, there are some geodesics that go and fall into the black hole. But if you're far away from the black hole, you can also think in Newtonian terms. The black hole is a massive object, so it attracts other objects by the gravitational force.
And another question, sir. How can mass be added to change our angular momentum?
No. Mass is not added to change angular momentum, but what happens is the black hole might itself have angular momentum. So remember, here in the laws of thermodynamics, we write a minus PdV term. And, we might also write a term which looks like, angular momentum times angular velocity. We might also write a term that looks like minus L d omega. If you do thermodynamics and you think of a system that doesn't just have volume, but maybe also has angular momentum, so that's a measure of the work that was done. So when you do some work on a system, the internal energy changes. There's a TdS term, but there's also work. So the PdV term tells you how much work was done in the system. So mass. So here what's happening is if you have a black hole with angular momentum and you throw something inside, you have to add the usual work terms, which is that when you can change the energy of an object by doing work on the energy. So those terms are always there. But in the case of thermodynamics, we have this additional thermodynamic term, which is TdS, which is important to keep track of. And so the work terms are the same as the first law of thermodynamics. There isn't a PdV term because you don't have, black holes don't have a notion of a well-defined volume and pressure. But the other work terms exist. And, the analog of the TdS term is the kappa dA term. I hope that answers the question.
Thank you, sir. Thank you, sir.
Okay. So please wait till the end. Don't ask too many questions now. Otherwise, you'll not be able to complete the presentation.
It's okay. I'm happy to hear.
Okay.
Okay. So there's this analogy between the laws of black holes and the laws of thermodynamics. And, people knew this. Now, people have known this for 50 years. And when this was first discovered, people thought about this in the spirit of Feynman's, Feynman's. I don't know. If you looked at the Feynman lectures, Feynman has a chapter in the lectures which is called "The Same Equations Have the Same Solutions." So, Feynman points out that if you look at, a mass on a spring and, some inductor and capacitor, then, those systems of an inductor and a capacitor and a mass and a spring satisfy the same differential equation. Therefore, they have the same solutions. So this often happens in physics. However, we don't think that an inductor and a capacitor is a mass and a spring. We just think it satisfies the same equations. So what I showed you right now is that you look at the black hole, which is on the left, it satisfies the same equations as this cup of tea that I have. Oh, my video was off. As this cup of tea that I have, and you might have thought that that's just another example in physics where you have two very different systems which satisfy the same equations, but that's not indicative of something really. It doesn't indicate that black holes really are thermodynamic objects. However, it turns out that Hawking found that when you add quantum mechanics to black holes, then something interesting happens. And that is that when you look at the horizon of the black hole, this is one way to explain it. This is not a very precise way, but I'll just say it in this language because it's commonly used and it's not completely incorrect. There are vacuum in quantum mechanics. If you look at the vacuum itself has fluctuations. And in particular, these vacuum fluctuations also exist near the horizon of the black hole. And these vacuum fluctuations you can think of as constantly leading to pairs of particles or virtual particles that are produced and that annihilate. However, what happens at the horizon is if you have such pair creation across the horizon, then one of these particles can go off to infinity and its pair can fall into the black hole because it's behind the horizon. The net result is that if you look at some observer who's far away from the black hole, they just see a steady stream of particles that's emerging from the black hole. And the steady stream of particles has a spectrum that's the same as the Planck black body spectrum. And so it looks like black holes really have temperature. So Hawking, this is a picture, it's a cartoon again. So remember, it's a slightly, it's an exaggerated cartoon. Remember, I said there was a horizon, but now once you add quantum effects, you have to change the picture that you had. The horizon is not just, some region of space where nothing is happening. Rather, you should think of the black hole as something that's also emitting radiation, and that's shown by this ring of fire, which I tried to show, which is kind of sitting at the black hole and it's emitting radiation. So the black hole is not really black in quantum mechanics. The black hole, in fact, emits radiation in quantum mechanics. And this is a discovery that Hawking made about 50 years ago. And you can compute the spectrum of the radiation. And as I said, the spectrum of the radiation is exactly the Planck black body distribution. And you can compute the temperature of the black hole. And the temperature of the black hole is given by some constants. But what's important is it's inversely proportional to the mass. So if you have a black hole that's very big, the temperature is very small. In fact, it's 6 into 10 to the minus 8 times m sun by the mass of the black hole in Kelvin. That's the temperature of the black hole as Hawking computed. Okay, so this was an important discovery, but what it told you is that this analogy between thermodynamics and the laws of black holes was not just a formal analogy, but rather it was something very real, and you should take seriously the idea that black holes have a temperature. Now, this discovery of Hawking led to something else that was interesting. You see, the total energy in the black hole is just by the famous formula that we all know of, mc squared, right? Which is m is the black hole. But now I told you that energy is lost through radiation. Therefore, the black hole is constantly losing energy due to these quantum effects. And that is basically just given by the Stephen-Boltzmann law. So it's sigma t to the power 4. There are some additional constants here that come due to what are called the gray body factors of the black hole. But, roughly speaking, that just changes this constant. And of course, there's the area of the black hole that tells because there's radiation coming from all over the horizon. But this tells you because energy has to be conserved, the mass itself has to decrease in a factor is proportional to t to the fourth. And if you put in the factors that I told you, remember t is 1 over the mass. And so this is 1 over mass to the fourth. The area is r squared. R is the horizon, which is proportional to the mass. So this gives you a factor of m squared. And you get a factor of 1 over m squared. And it tells you that black holes lose mass at this rate. Okay. Now, this is an interesting effect because it tells you that if you wait for long enough, then the black hole evaporates completely. How long does it take for it to evaporate? You can compute, and it's roughly of the order of 10 to the minus 16 into the mass of the black hole in kg cube. Actually, a very large number. For instance, you remember that the mass of the sun is about 2 into 10 to the power 30 kg. So if you put that factor here, then you will find that a solar mass black hole takes 10 to the 67 years to evaporate. And as all of you know, the age of the universe is only 10 to the 13 years. So effectively, for all effects and purposes, a solar mass black hole is an eternal black hole. It does not evaporate. There's no sense in speaking of the evaporation of a solar mass black hole. But as I was saying at the beginning, there is nothing that prevents the existence of black holes that are much smaller. So if you take, sometimes people ask me about the Bermuda Triangle, and I give this talk, and if there's a black hole in the Bermuda Triangle. But imagine there was such a black hole that swallowed up a jumbo jet, a plane, and a plane has the mass of 400 tons. So a black hole with a mass of 400 tons, you can compute by the same formula, would in fact evaporate in about 5 seconds. So that would be a human timescale evaporation. So indeed, if you look at black holes which are much smaller, and as I said earlier, there is nothing that theoretically prevents the existence of such black holes, then they would evaporate in a finite time, and they would really cease to exist due to these quantum effects. So if you think of, this black hole that I mentioned, so as I said, we want to think of black holes which are kind of isolated. So we have this black hole, which was maybe earlier a star, or maybe it was a very small star because we want to let it to evaporate very fast. And then, the star collapsed into a black hole. And then because of quantum effects, we started getting this radiation. And therefore, after a long time, what remains from the black hole is only the radiation and not the original star. So all the physics that we understand suggests that you can have stars, they collapse into black holes. Those black holes later turn into radiation. This led to what is a very famous paradox in physics, which is called the information paradox, which goes as follows. It tells us that, you take one star, maybe it had more hydrogen and less helium, and you collapse into a black hole. And you take a second star which had the same mass, maybe it had less hydrogen, more helium, or maybe it had more carbon. It collapses into a black hole of some mass. But remember, in the description I was giving you, I was telling you that what's produced at the end is just some black body radiation. But the black body radiation doesn't seem to have details, only seem to care about the total mass, and didn't seem to care about whether the star had carbon or hydrogen or helium or what. And therefore, it suggests that both these stars, if they had the same mass and they collapsed into black holes, would lead to the same radiation. And Hawking argued that this process meant that the time evolution arrows would not be reversed, and this suggested the breakdown of unitary evolution in the presence of gravity. Because remember, a very important principle of physics, both in quantum mechanics and in classical physics, is that you can always reverse time evolution. Remember, we teach our students, often we phrase a question saying, if you throw a ball up with some force or some velocity, where will it land? But in fact, you could have asked the students the opposite question, which is if you said a ball landed at this velocity with some, at some time, where did it originate from? And you can do the calculation not only forward in time, but also backward in time. And this is a very basic property of all the physics that we know, quantum mechanical and classical, which is that time evolution is always reversible. You can run it one way and you can also run it the other way. And what Hawking suggested was that this would break down in the presence of black holes due to these quantum effects. So this is what is called the information paradox. Okay, so now I'm going to go to the last part of what I had to say. But if there are any questions here, I'm happy to take them. Otherwise, I'll say some more. I'll talk about some more our recent or modern understanding of how we think of this. Yeah. Is there a question?
Continue. So they will ask questions maybe at the end.
Okay, fine.
Yeah.
Okay, what is the answer? How do we now understand the information paradox? So there are two aspects to the answer. Let me explain one, and then I'll explain the other. The first is that, Hawking was really looking at this thermal radiation, but he was not looking at, his calculation was not precise enough to look at correlations between different parts of the thermal radiation. This is what I have drawn here is a cartoon. It's just a cartoon of some black dot which suggests a black hole, and a set of random dots. These are really computer generated to be random, which are red, blue, yellow dots, and they're random because they're random dots. You might have thought there's no information in them. However, if you look closely, just in this cartoon, what I want to show you is there's in fact a correlation, which is that if you take a purple dot and you draw a line and you go to the other side of the black hole, you'll find a yellow dot. And you take a red dot and you draw a line, and to the other side of the black hole, you'll find a blue dot. The only point here I'm making, which is a trivial point, is if you look at the joint probability distribution of these different dots, that joint probability distribution has some correlations that the individual marginal probability distributions don't. If you just look at the probability of any given dot, it's some random probability, it's some thought process. But when you look at the joint probability distribution, you'll find there are some correlations in this. And in fact, these positions of these are correlated. So these joint probability distributions can encode information that just looking at, the marginal probability distribution cannot. And Hawking's calculation, in fact, did not account for these joint probability distributions. And one can show that very fine-grained correlations, if you have a lot of different variables, then very fine-grained correlations between those variables can capture information, can capture a lot of information. So, it looks, that is the first level answer to the information paradox, which is that if you look at very fine-grained correlations in the radiation that emerges from a black hole, then that captures information about what fell in. This is not different from what happens in our everyday process of thermalization. If I take the tea here and I swirl it a little bit, after some time, it will look like it's dissipated. So it will look like, everything, the information about how fast I swirled it has dissipated. Of course, we know that's not true. What has really happened is the information has gone into the, atoms and molecules of this cup, and it has gone into the atoms and molecules of the air. And if you keep very careful track of all that information, you will be able to recover what happened to the tea as well, what I had done with the tea. And so at first order, the answer to the Hawking radiation is just that, the answer to Hawking's paradox is just that, the black hole serves as an efficient shredder of information. So it shreds the information that fell in. But, what it creates are some very fine-grained correlations, but it doesn't really destroy information. However, there is a second, more sophisticated question that one could ask, and this will bring us back to some of the things I said at the beginning of the talk, which is that it looks like the radiation from a black hole emerges from the horizon. But the horizon doesn't have the infalling matter. The infalling matter looks like it has fallen in. So how does the horizon have information about the black hole? So I said that the answer is that the information about what star was there initially is preserved in these fine-grained correlations in the radiation. But you could ask, the radiation that I described was formed from the horizon, but the horizon really looked like empty space. So even if it has fine-grained correlations, how did those fall? This leads us to something which is, I think, a rather deep property of quantum gravity that we've discovered. And in fact, this is something that we discovered in work at ICTS over the past several years. And this property is what we call the principle of holography of information. And it tells us that in a theory of quantum gravity, whenever you have a bounded region like this blue region R, then, and the complement of the region therefore surrounds the region, then all the information in the bounded region is also available outside the region. And this is due to effects of quantum gravity. So it's not true that you can hide information in a bounded region. Whatever information is here, in fact, also exists in correlations of the metric and other degrees of freedom outside. Okay, so now you might ask me, why would we believe that such a property is true in quantum gravity? And I'm going to give you not a proof. Of course, I can't give you a proof in this talk, but I'm going to give you some physical understanding of why quantum gravity has this very unusual feature that information in a bounded region is also available in its complement. Okay, before I do that, let me just say that you see that this gives us a resolution also to the information paradox, even to this more sophisticated version, because it tells us that if you have observers who are outside the black hole, they always have information about what fell in. They always have a copy of the information that fell into the black hole. Therefore, information is never lost. And there's no surprise that Hawking radiation, which is produced at the horizon, or that's produced here, has information about what fell in. Because remember, I'm telling you that in a theory of quantum gravity, in the region outside a bounded region always has information about what's inside. So now I want to tell you why you should believe that something like this should be true in quantum gravity. Okay. So I'm going to take you back to something basic about quantum mechanics that all of us are familiar with and all of us teach, which is the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle is usually phrased as a relation between the uncertainty in momentum and position. However, you can also think of it in terms of energy eigenstates. If you think of an eigenstate of energy, then an eigenstate with a definite energy always has indefinite location. It's always delocalized in position space. Now, this doesn't prevent us in quantum mechanics from creating localized objects. We think this cup is localized here. It's not delocalized everywhere. And how do we do that? Well, we do it by superposition. This is what we teach our students. We take an energy eigenstate, we add another energy eigenstate, we add a third different energy eigenstate, we add some phases to those energy eigenstates. And if you arrange those phases and these superpositions correctly, then you can engineer to have destructive superposition outside a bounded region and constructive superposition inside that region. And therefore, you can arrange for a wave function that has the form that it's non-zero here and zero outside. So far, what I'm saying is just straightforward quantum mechanics. It has to do with how you generate localized wave functions in quantum mechanics. Now, what is different in gravity? Well, what is different in gravity is in fact something very familiar again, and something again that we teach in undergraduate gravitational physics, which is that in a theory of gravity, the energy can be measured from infinity. So this is another version, another statement of the force law, as you remember, can also be made in terms of the Gauss law. The Gauss law tells us that if you look at the flux of the gravitational field at infinity, then the flux of the gravitational field at infinity is equal to the mass. Now, the Gauss law is in fact also true in general relativity. In fact, you can say it's more true because the only definition of the energy that we have in general relativity comes from the Gauss law. It comes from saying that you compute the flux of the gravitational field at infinity, and that is really the only good definition of energy that we have. So in a theory of gravity, it's a very important feature that you can make measurements at infinity, and they can let you measure the energy of an object inside. In fact, that's how we know the mass of the sun. Sometime back, I said that we know the mass of the sun is 2 into 10 to the power 30 kg. But of course, none of us has been to the sun. The way we know it is because we know the gravitational field and we can integrate it over a Gaussian surface. And using that, we can determine what the mass of the sun is. So what is special when you combine the two principles I mentioned, which are the principles of uncertainty principle and the Gauss law? Well, it tells you, first of all, that due to the Gauss law, you cannot just speak of, imagine you have some matter and you also have gravity. Now you want to treat the matter quantum mechanically. But quantum mechanically, it is not possible to just imagine the matter in some energy eigenstate. It must necessarily also have a gravitational field. This is sometimes called a gravitational tail. And that is because if you put the matter in some energy eigenstate, you have to ensure that the Gauss law is satisfied. And so the flux of the gravitational field at infinity must be equal to the energy of the eigenstate that you have. So when you think of wave functions in quantum gravity, one very important feature is that when you think of energy eigenstates, you cannot just think of energy eigenstates. You also have to think of the gravitational field, and in particular, the gravitational field must be constrained so that the Gauss law is satisfied. Good. Now, what does this have to do with the failure of localization? Well, now imagine doing this process again. Remember, I told you, how we localized objects in quantum mechanics. It was by means of superposition. But now imagine playing the same game in a theory of quantum gravity, where you want to create a localized excitation so that you can hide information in a bounded region and not have it leak outside. Well, now you're in trouble because you take the energy eigenstate and it must be dressed with this field, the gravitational field. You take a different energy eigenstate, but this different energy eigenstate, sorry, or did I switch on something by mistake? Anyway, but this, sorry, I think I have switched on this transcription. I don't know why. I didn't.
That's okay. No problem.
Okay, fine. Anyway, so you take one energy eigenstate, it must be dressed with a gravitational field. You remember I said you had to superpose different energy eigenstates. You take a different energy eigenstate, it is dressed with a different gravitational field at infinity. So the gravitational field at infinity due to the energy eigenstates is different. Now you try and superpose them. And remember, in quantum mechanics, without this gravitational field, you just superpose them, right? You didn't worry about this field. But now in the presence of quantum gravity, when you superpose them, the existence of these tails prevents destructive interference outside a bounded region. And in fact, you can prove, of course, what I've given you right now is not a proof, that correlation functions of the energy and other observables carry information about the state. And in fact, any state is uniquely specified by giving me the gravitational field and other correlators outside. Okay? So in particular, in a theory of gravity, in a non-gravitational theory, you can think of a setup of this kind, where you have some information or some excitation inside some bounded region, and to an observer outside, everything looks exactly like the vacuum. What is more, in a theory, in a non-gravitational theory, you can change the form of the excitation in a bounded region. In fact, this is what we mean when we talk about information. You can change the shape of this bump while still keeping things completely unchanged outside. Of course, eventually, if you wait for some time, light will propagate from here to here. But at that instant of time, you can always prepare such states. In classical gravity, first of all, you can't even prepare a state where you have an excitation in a bounded region and nothing outside. Because even in the classical theory, there's a Gauss law that tells you that you're sensitive to the mass. But in the classical theory, you can rearrange the mass in a region while keeping the gravitational field outside the same. In the quantum theory, you cannot even do that. So if you look at the details of the gravitational field and other quantum mechanical observables outside, they're completely sensitive to the details of the matter field in this region. Okay? And this is why in a black hole as well, the region near the horizon, in fact, retains a complete copy of the information that fell in. And that is how Hawking radiation, in fact, knows about the information that fell in. So that is the answer to the question that I phrased at the beginning about how information emerges from a black hole. And the answer is that as a result of these effects, the region outside the horizon is not free of information. Okay, good. So let me just summarize. There were two things which were unusual. There were 2 points which are important in resolving this information paradox. One of them is that there are rather two errors in Hawking's argument for information loss. And one of them is that, Hawking computed these simple observables, which was the spectrum of the radiation. But just because simple observables look thermal doesn't mean the microscopic state has lost information. This is the physics of thermalization that we study in statistical mechanics anyway. But there's a deeper effect, physical effect, that's important for black holes, which is that quantum gravity localizes information very differently from classical gravity and non-gravitational theories. This goes by the principle of holography of information that we have understood, in fact, here in the past several years. And this helps to now completely resolve this paradox because it tells us that the region outside the horizon is not free, is not information free. Okay, so let me stop. This is the last slide I have. I want to end on a slightly philosophical note. The way I started this talk was by saying that, we had a very successful theory of gravity, which was a Newtonian theory, which had the sun and the earth and had action at a distance. And we said, we don't like action at a distance. We want exact locality. And so for that reason, we created this general theory of relativity where we had all this framework of, this fabric of space-time. And the reason it was done, as I motivated, was really to get a local theory. But now you add quantum mechanics and you think a little bit more, and you realize that locality is not so simple in quantum gravity, but rather in quantum gravity, there is this feature that information in a bounded region is always available outside. Of course, it's not action at a distance as in the Newtonian force law, but it gives us a sense of the progression of our perspectives on gravity and space-time. Okay, so thank you for your time. I'm sorry for going a little over time. I'll stop here and we can take questions.
Okay. Thank you very much. Now there's time for some questions. Can I begin with a few questions?
Yes, please.
Yeah. When you were discussing the Hawking radiation, you explained it as the kind of a pair production happening at the horizon, and one particle getting into the black hole, other coming out, that leading to the presence of so-called black body radiation.
Right.
My question is how these particle emissions can be understood are related to radiation emission,
Yeah. So, roughly, so, this analogy should not be taken very seriously.
I thought so.
But this analogy is roughly the physics is as follows. Imagine that you have virtual particles which are produced on opposite sides of the horizon.
Yes.
Then the particle which is outside the horizon, stays outside, but the particle which is inside the horizon falls into the black hole.
Yeah.
So if you have particle production at the horizon, usually what would happen is that these particles would particles would form, and they would recombine, and so you would have some virtual particle production, and they would just recombine. But because they are at the horizon, due to the gravitational field, one of them is outside and stays outside, and the other, which is inside, stays inside and it falls inside. So that's one way to think about what's happening, which is, you have these correlations or this formation of particles across the horizon, and the one which is inside the horizon just falls in. So if you're an observer outside, you just see the stream of particles which are coming out because you don't keep track of the particles that have fallen in. And that's why for an observer outside, it looks like you just have the emission of particles.
Emission of particles, I understand. But what about radiation? Where's the radiation coming in?
So radiation is emission of particles. Photons are particles. So by particles, I just meant, radiation is, in fact, the particles that are produced, if you look at the Planck blackbody formula, it tells you that the rate is exponentially damped with the energy. So the particles that are produced the most are photons and gravitons, because photons and gravitons are the ones which can have the lowest possible energy because they don't have any rest mass. If you look at other massive particles, like say electrons and other such stuff, they have a lot of rest mass. So already their production is exponentially damped. And so when I spoke of particles, radiation, that's just particles as well. So the black hole will emit, electromagnetic and gravitational radiation, by which I mean photons and gravitons. And that's in fact the dominant mode of radiation.
Oh, you also mentioned about the black hole evaporation leading to black body radiation.
Yeah.
So can it account for the CMBR, any component of CMBR by any chance?
that's not how we think of the CMB in general. We might now generally we think of the CMB as originating from a slightly different process, not by originating due to black holes. Now, one could ask the following question. One could ask, if there were a lot of black holes in the early universe, you know, could those black holes lead to some fluctuations within the cosmic microwave background radiation? So
That's what I meant. That's what I meant. Some component of this black hole evaporation.
yeah.
Could it
So
be there, and could it be isolated from the normal stellar CMBR component?
yeah, so that's a question people ask. We don't know the answer. It could be that if there were a lot of black holes in the early universe, which in fact evaporated. You see, the black holes would have to be much smaller than stellar mass black holes. But if you took a lot of black holes which were formed due to some mechanism in the early universe and which evaporated, then they might give rise to an observable signature in the CMB. We have not seen any such signature. We don't have any such evidence so far, but it's possible that something like this, might be observed. So there are proposals and speculations that maybe you might be able to see something like this in the CMB.
So there's a question in the chat box. It says,
Yeah.
can you speed up the radiation by gravity?
Can you speed up the radiation by gravity? I'm not sure that means. Can you?
That is the velocity of whatever light or any kind of signal.
If you ask, can you speed up the radiation by gravity? If you ask the friendly giant to hold a mass fixed outside the horizon, no. Actually, the radiation is no. So maybe the question is, can you somehow attract energy outside by holding a mass?
Yeah.
Not really. You can't actually pull out energy from a black hole in that way. So this black hole this radiation that's coming out is coming out due to quantum fluctuations. And okay, of course, you could try to modify the quantum fluctuations. In fact, that's a question I don't think which has been answered in detail. When we compute these fluctuations, it's a hard calculation. So the calculation is in fact usually done by imagining that the matter has fallen in and you're at late times. Now you could ask, how would the rate of evaporation change if there was something else in the vicinity of the black hole? In fact, I don't know the answer to that. I don't know if that calculation has been done. Sounds like a hard calculation. It's an interesting question. So maybe, it's a calculation which works good.
There's a question by Ashoka. Ashoka, what's your question? Can you ask your question? Ashoka, you can unmute and ask your question. Okay.
There are some questions from audience.
No, Rudaswamy. Okay, Rudaswamy.
Yes, sir. Yes, sir. Yeah, very informative talk on black holes and gravitation. I have a couple of questions. How many black holes are discovered so far? What is the mode of their discovery? Do we have black holes existed in our solar system? These are the questions.
Yeah. Many black holes have been discovered. I don't know how many, but many have been discovered. There are basically two ways in which we discover them. One of them has to do with the fact that if you have black holes which are very far away, like Sagittarius A star, which is in the center of the Milky Way, you can look at the orbits of other stars around them. In other cases, in the case of black holes, what happens is if there is gas in the black hole that's accreting and that's falling into the black hole, as the gas falls in, it emits radiation, and that radiation can be detected. And by seeing that radiation, we are able to determine that there was a black hole there. So there are many black holes which emit electromagnetic. The black holes themselves don't emit, but due to the strong dynamics of gas and stars in their vicinity, that leads to electromagnetic radiation that can be used to understand that black holes exist. The second way in which black holes can be detected, of course, has to do with the talk that you had last week, which has to do with gravitational radiation. And gravitational radiation is also a very effective way of detecting black holes. In particular, when black holes collide or black holes collide with neutron stars, you can detect the gravitational waves that are produced from that. So we've detected many black holes using these methods. There are no black holes as far as we know in the solar system. But of course, if there was a very small black hole somewhere, then we wouldn't know it. But there's no big black hole that we know of in the solar system.
Okay, Raman, SV Raman, you have a question?
Yes, sir. Some audience are asking questions.
No,
Even though in real, we haven't found a white hole, But would it be appropriate to say that white hole lies behind a black hole with wormhole in between them as a connection, like a hourglass? This is the question, sir.
No, the hourglass figure actually doesn't say that a white hole lies behind a black hole. So I think maybe someone is thinking of this picture of what's called an eternal black hole. And a white hole is a solution of a black hole which is reversed in time. So one way, you can think of a black hole as a setup where you have thermalization occur. You have some gas of dust, and the gas of dust collapses to form a black hole. Now, in fact, you can have, as we know in physics, you can always, if you have a certain kind of solution, you always have the reverse solution. So the reverse solution is also a solution of the equations of motion, where you have some setup where suddenly, there's some object and suddenly a gas of dust kind of explodes and comes out of it. Okay? That is like saying a little bit like, when you throw a stone, you can throw a stone, it leads to the formation of ripples that spread out from where the stone fell into the water. And then the stone is gone behind the water, right? But there is also a solution of the equations of motion, as we all know, where the ripples all converge and suddenly they throw a stone out of the lake. Now, we don't observe that because statistically it is very unlikely. We don't observe that because of the second law of thermodynamics, which tells us that it's easy to set up initial conditions where you can throw the stone into the water, but to set up a condition where all the ripples converge and throw a stone, that's why none of us has ever seen that we are just standing on a lake and suddenly, some ripples converge and a stone comes out of a lake. It's a solution of the equations of motion. There's nothing, but it's a very unlikely event to happen. Therefore, the same reason we have not seen white holes. It's exactly the same. The same reason that we never stand on a lake shore and see stones coming out by ripples converging. We don't see white holes because they're statistically unlikely objects. In the eternal black hole solution that you're thinking of, actually that solution is slightly different. The way you should think of that solution is that you have a black hole that has two mouths. It has two horizons. So there's one horizon which is in our galaxy. This is the question. And you fall into that horizon, but there's another entrance to the black hole, which might be in some very distant galaxy. That's what's called a wormhole. So, we are in this galaxy, there's somebody else in a very far away galaxy. We both jump into the black hole and we'll actually meet inside. So there are two doors to the black hole, but when you enter, it's the same room inside. It's the same black hole inside. That's how one should think of it. Of course, we won't be there to report to people outside because we'll all both die. But if you just wanted to meet once and were willing to sacrifice, we were both willing to sacrifice our life to meet, then we could both jump into the wormhole and meet. And then so yeah. So that's
I have
what
one
the
question.
solution means. Not that there's a white hole, but that there's another entrance to the black hole somewhere else. That's
Okay, here's a question by Ashoka.
Ashoka is asking.
Yeah,
No,
question.
sir.
Yeah,
Excuse me.
make it brief.
The movement of a heavenly body is due to what?
The
Motion of a heavenly body is due to what?
He says motion of heavenly bodies is due to what force?
Is due to what?
Heavenly bodies means what? I mean, planets
A
and
sun
stars.
or a star or a
Planets, sir.
or a planet like
Gravity.
Earth.
Yeah, gravity. It's due to the gravitational force. That's what I said at the beginning. That of course the gravitational force was, discovered first by looking at the motion of heavenly bodies. But what I was saying was, in the modern theory of general relativity, we don't think in terms of a force. Rather, we think that the sun warps the space-time around it, and then these bodies are moving in geodesics in that space-time. But the gravitational force is a perfectly good way of understanding the motion of celestial objects, which is that the sun and these objects exert a different force on each other. And, that force is proportional to the mass product of the masses and inversely proportional to the square of the distance. And each of those bodies feels the force of the other bodies, and that's why they move.
Okay, and thank you very much, Professor Raju. Now,
Yes, sir. I have
now
two doubts.
Okay, now
You mentioned about the lifetime, that is about 10 raised to 67 years.
Yeah.
Another thing you also mentioned about the mass. But is there any idea about the temperature inside, and also is there any nuclear fusion in any black hole?
Yeah. The 10 to the 67 years I mentioned was, only the lifetime of a solar mass black hole. Different mass black holes will have a different lifetime. As I said, if you take a much smaller black hole of lifetime 400 tons, for instance, it will have a lifetime of 5 seconds. In the earlier discussion we were having, people sometimes think of primordial black holes that might be maybe 10 to the 15 kg. And then they might have evaporated in the early universe, and we could ask, are there signatures in the background? So 10 to 67 years is just an example for a particular mass. The general formula is that it's constant times the cube of the mass. If you put in mass of the sun there, you'll get 10 to the 67 years. You put in different masses, you'll get different lifetimes. That's the first point. The second point was, is there nuclear fusion? So generally, the way we think about the black hole is that, when there is, of course, fusion that's in the star, that's stopping the star from collapse. When that fusion stops, then, there isn't that radiation pressure, and as a result, the gravitational force starts dominating and the black hole is formed. But once the black hole is formed, at the horizon of the black hole, there's really nothing, as I said. At least classically, there's nothing. Quantum mechanically, there might be radiation emerging. But classically, there's just nothing at the horizon of the black hole. So it's not that there is fusion or there's something dramatic happening. It's just empty space at the horizon of the black hole.
Professor Kagli, can I ask a small question?
Yeah,
Yeah,
okay.
please go ahead. Yeah. For me, it's fine. Yeah.
Okay. Professor Raju, the question is, if a huge black hole is formed closer to solar system, can it suck any of these planets or the whole planets in the solar system?
Yeah, but of course, such a black hole cannot be formed because we know, it's actually related to this fact. We know that there isn't the same kind, this mass is not there near the solar system, right? We know that so for such a huge black hole to be formed, there would have to be a lot of mass. But there is no such mass near the solar system, right? We have looked around and we don't feel the gravitational force of that. So when the black hole is formed, the gravitational force doesn't change. If the sun were to become today, we would not feel any change in the gravitational force. Of course, we would stop being able to see the radiation from the sun. The gravitational force would not change. So a black hole cannot suddenly be formed outside the solar system. Now, what you could ask is, could a black hole kind of come from some other galaxy? And I mean, something like that could always happen. More likely than a black hole, some asteroid could come and hit us. But of course, it is possible that a black hole could come from somewhere else and swallow up the whole solar system along as it comes. But, yeah.
Thank you very much. Thank you.
I heard about some speculation saying that singularities don't form if you take into account the quantum fluctuations. What do you think about that?
Horizons don't form, the black holes
No,
don't.
not for a singularities don't form because of quantum fluctuations.
Yeah, so indeed it is believed, the general dogma in physics is that singularities are just a case where we don't understand the physics well. We don't really think that there's a singularity anywhere. And indeed, it could be that due to quantum fluctuations, singularities are somehow resolved. So what we would think is that, you have some matter, it becomes very, very dense. And the theory of general relativity predicts that a singularity will be formed. But in fact, what happens is that we have to correct the theory in those regimes. And then in the new theory, you don't form a singularity.
Start forming particles to be there.
So this is
strong gravity.
Yeah, so this is based on the general idea that in physics, you never really have singularities. Whenever you think there's a singularity, there's in fact a way of thinking of it in a smooth way. So, that's what we would like to think but we don't really understand how to resolve the singularities of these black holes. So there are some theories about what happens to a singularity, but there isn't something very sharp to say. What I told you about, localization of information in gravity, I think is very robust because we can really derive it based on very few assumptions. So this picture of information and what happens at the horizon is a very robust picture. It's something we learned about quantum gravity by thinking about black holes. But in the end, it's a lesson about quantum gravity that we have learned. So we have really learned something new about quantum gravity. We cannot say the same by thinking about singularities. We have not yet learned something new about quantum gravity because we don't understand singularities well enough. Maybe we will in the future, but right now we don't have anything to say about it.
Okay, thank you very much. Now I request our General Secretary.
Yes, sir. Thank you very much. In fact, you have given us an idea about how we can distinguish the black hole from the classical point of view and that of quantum mechanical point of view. And of course, I don't know when it will come to our textbooks about the quantum mechanical aspects of black hole. But only then I think we would be able to understand the real meaning of the black hole. But still then it will be only in the research field. Anyway, thank you very much. You have given us a very good idea about the black hole concept from the point of view of quantum mechanical picture. And I thank again all the participants, KPA members, and also the invitees. I think many have joined for this lecture. I thank all of them. And then from KPA, I want to thank Gnanadhara, Dr. M.K. Raghavendra, who is supporting this platform. Thank you very much, and thank one and all. And again, I think we expect you some more ideas about the black hole in future from you. Thank you very much, sir.
Thank you.
Thanks a lot, Professor Raju. Thank you. Now we are leaving.
Thank you, sir. Thank you.
Thanks a lot. Thank you.